I would say if we start from us on Earth, we haven't seen dark matter. And if we then go further out in the local universe, it doesn't seem that we need a lot of dark matter there either. So how come that suddenly, the farther away we go from our own position, where we have lots of data, how is it possible that suddenly, when we go far away, that we need a lot of data? That we need a lot of dark matter, or that we miss mass? Is it rather, I would say it could also be, well, possible that we are actually missing something in our models, that we are not missing mass, but just that nature is more complicated than we think, and the models that we have are not complex enough to capture that. I mean, you mentioned the bullet cluster. The bullet cluster is one of the famous examples where people said, this is the evidence for dark matter.
The smoking gun.
The smoking gun, in the literal sense, this is why it's called the bullet cluster, because you see that you have two big clumps of matter that have been merging, have been colliding, and then they fly away. So they flew through each other, and now they fly away at a certain distance. And then you see that you have in the X-ray signal, you have the baryonic hot plasma that also interacted in the collision. And then because there is a lot of physics going on there, like the plasma interactions and all of this, so this is the merger is then delayed for this X-ray signal. And then you see two bullets. One of them is really clearly like a bullet flying out again after this collision. And then people say, if we now take a look at the position of this X-ray cloud, or the two X-ray clouds, and the position of the galaxies involved in this merger, we see that there is an offset between the optical image that we have, and of course also the dark matter part that has been reconstructed from lensing again around these optically detected galaxies. This is one part, and this is offset to the X-ray signal that is the bullets and the gas cloud. And this offset then was taken as an evidence that here dark matter does not follow the luminous matter, the baryons, because we have this offset. So the total mass is not where the mass of the visible things are, mostly. This was propagated from 2004 onwards. And a recent study, just last year in 2025, there was a big NASA press release from Sang-Jun Cha et al. Pardon my bad Korean.
Sure.
And these persons, they had a look at the intercluster light, meaning all of the stars that are not bound into the individual galaxies of the cluster. So, because if you have a violent merger, then of course not any X-ray gas is emitted, but there are also like galaxies that lose their stars. And these stars, they go into a collective cloud of stars, which is called the intracluster light in the intracluster medium. And with James Webb, it became possible to track this intercluster medium because the infrared wavelength at which James Webb observes makes it now possible to look at this. And so they took a map of this gas cloud, the map of the stellar cloud, and they found that this merger is much more complicated than just two clumps colliding and moving apart again. They said it could have been that the biggest clump actually underwent an earlier merger, and then they saw that there was an elongated arm going in the direction of the merger. And so it wasn't just two spherical clumps colliding. There was no offset in that sense between the luminous mass and the dark matter mass, because all of the stars in this intercluster light were actually nicely following this merging structure. And so they said this cannot be a clear hint for dark matter is offset to luminous matter, and again refuting Mond. And so they said if we now take a closer look with new data that's actually possible now for the first time, we see we can reconcile everything we know with the new data here. So there is nothing spectacular that the dark matter would be completely detached here.
Interesting. I didn't know about that paper. So I'll place that paper on screen and the link will be in the description. And for those who are driving and just listening to this, maybe running or what have you, but you didn't see it and you were thinking, oh, I wish I could see the bullet cluster merger. Yes, you can. That will just rewind. We'll place the visuals of that on screen. Okay, so what's the reception to that paper been like then? I'm sure, as with anything, philosophy, math, physics, everywhere, there's usually counters to, not usually in math, sorry, in physics or philosophy, but there's usually counters to when someone puts up a position. So what's the counter there?
I haven't heard much about objections or so. I would rather think that I would say it's a clear evidence that this cluster is much more complicated. And this comes actually in a row of several other findings that have now become possible with better technologies and better data, that people say, okay, first, back in the 90s, and I mean, the first gravitational lens was found in 1979. And so we do not have that much experience in lensing when we go to 1990. So everything was pretty coarse-grained and preliminary. But now, today, after all of these years, we have a lot of data and we have a lot of experience with different galaxy clusters. So if we now go back to the findings of the earlier times and we re-look at all of these galaxies or galaxy clusters, we find much more detail. And this detail is then the thing that resolves the puzzle. Like, for instance, here in the bullet cluster, we have this the intercluster stars, which now resolve the discrepancy between dark matter and luminous matter. And the same happened for a galaxy cluster that my team and we were investigating. It was Abell 3827. This is another very beautiful galaxy cluster. And in the center, you have 4 luminous galaxies. They're almost equally bright. And from this very unusual configuration, it's pretty obvious that this is a dynamically very active cluster. Normally, people like to look at galaxy clusters that are relaxed, as we say, meaning we have one brightest cluster galaxy, and the rest is then just nicely, hopefully, isotropically distributed. So the ideal case would be a spherical galaxy cluster with one very bright galaxy in the center. But this one here is exactly the opposite. 4 luminous galaxies in the center, and then we have strong gravitational lensing around these 4 galaxies. And this lensing almost forms a complete ring. This was why it was such a really beautiful, huge gravitational lensing event around these 4 galaxies. So people had a look at this, and then it was pretty obvious at the start when you do forward modeling, you need to impose a lot of dark matter. And when you reconstruct your total mass distribution with such a model, you find again that the dark matter seems to be at different places than these 4 luminous galaxies. And there, it was exactly the same process. People first thought, this is an evidence that dark matter and luminous matter can be decoupled from each other. So what physicists call light does not trace mass, meaning you can have the luminous stuff at a different position. And then people first thought this was yet another bullet cluster. But with more and more observations, you could see how this discrepancy was shrinking, even in modeling. And then my colleagues and we analyzed this cluster with our model-independent approach. And there we could definitely prove that this offset between the luminous part and the dark matter part was completely driven by the models. And this is the perk of our approach, that we can say we have a look at the local lens properties, and we can track how fast these properties change over our multiple images. So we had huge multiple images in this case. It's a very beautiful example. And in each multiple image, we found star-forming regions. And so we could use these star-forming regions to chop up each multiple image into several parts. And then we mapped only these parts onto each other in all of these multiple images to get the local lens properties. And so we saw that over the area of the entire multiple images, the properties were changing. And this for us meant, okay, our approach relies on the fact that over a certain area that we look at, that the properties do not change. So we assume that we have constant properties in the area where we look at. And if we now have patches across a multiple image and we see each patch has a different property for this local lens property, that each patch gives us a different value for a certain local lens property, then we know, okay, for instance, the mass density needs to change or the distortion strength needs to change over the multiple image. And this means the lens is quite turbulent. It's changing. So if we now assume we have a huge dark matter halo that is smooth and hardly changing, then we can see that this is not fitting the actual reality that is given by the data. And so we could say, if the mass density already changes over a single multiple image, how can we extrapolate this lensing properties into a region that is much farther away from these multiple images than just an epsilon, than just the individual patches that we aligned together?
The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new Insider feature. It was just launched this month. It gives me a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high-quality podcast. Something else you should know about is that if you go to their app, they not only have daily articles, but they also have long-form podcasts with their editors and writers. This is also available online. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount.